when we were discussing who would be best to really talk about wearable sensors and application in sport, it was really a no-brainer for us. We just needed to see if she was going to be able to be available at 6 a.m. in the morning, Western Australia time. So I'm very proud to introduce Dr. Jacqueline Alderson as Associate Professor of the University of Western Australia. She's certainly published extensively in wearable sensors for sport application. Jackie, we're very grateful to have you here with us. Hopefully you do have that cup of coffee with you. But very much looking forward to hear your presentation. So Jackie.
Thank you very much, Bryson. I'm assuming everyone can hear me. I've had one coffee already this morning, and I'm hoping I'll be able to get through this for you, calling in from the future, 6 a.m. Friday morning. So thank you very much for the introduction and the invitation to talk today. It's going to be a little bit different. I suspect you've been having a deep dive for the last couple of days inside baseball proper. So I'm going to take you a step back, if you like, and we're going to start having a bit of a conversation more generally about perhaps wearables, but more so data and computer vision, where I'm actually spending quite a bit of my time now, if hopefully nobody minds about that. So for those of you who, there's a little bit of a, here we go. For those of you who don't know me or the University of Western Australia, you're probably a bit distressed to see the word cricket on the screen now, but I think it's quite relevant for me to just give you this little bit of a background with respect to how I came into inertial sensors and wearables. It's less to do with baseball and much more to do with cricket and the rules surrounding cricket with respect to illegal action testing, which dates back to about 1995. When the University of Western Australia and I became involved in that, and we were lucky enough to have a very long and colourful relationship with Vicon since the 1980s. So they've been solid partners through this time with us as well. So over the last 25 years, we've spent a significant period of time developing upper limb biomechanical models. And particularly with respect to understanding the role of the elbow joint. And I understand completely that we're not talking about baseball here, and I know that they're not the same thing, and I'm going to explain to you exactly why they're not the same thing with respect to why we've actually been spending so much time trying to understand and model the upper limb appropriately. And so for those of you who are not familiar with cricket, I'll just let you know essentially what we're looking for in the rules of cricket, and this is really to make it as distinct from baseball as they can, is that you're not allowed to extend your elbow. So there cannot be any level of elbow extension greater than 15 degrees. And as you can imagine, trying to model that during fast-moving dynamic motion, and you've got soft tissue artifact, etc., is very, very difficult. The person you can see on the screen right now is Shoaib Akhtar. He was one of the early individuals who was called for an illegal bowling action. And he actually presented with, as you can see there, about 42 degrees hyperextension. So we had to actually spend a significant number of years working out exactly how to properly model hyperextension when he was bowling at about 160 kilometres an hour. And remove that from that extension threshold. So the anatomical relevance of modelling the upper limb appropriately became paramount. And the person you can see in the bottom there, when I was clearly a lot younger, is Mutai Muralitharan, who's the world record holder in cricket. He's a spin bowler. He had the opposite problem. He had a fixed flexion deformity and a carry angle of about 40 degrees and a fixed flexion deformity of about 38 degrees. So both of these two individuals were deemed to be in the spirit of technically bowling with an illegal action, but in order to allow them to play, we made a case on both occasions that Murali himself was not actually extending more than 15 degrees, but for Shoaib above there, we made a case that it was not in the spirit of the law to ban him for hyperextension because it was non-volitional in the sense he couldn't control it. And it's that background really, I really just wanted to cover briefly, just to give some landscape as to why we've spent so much time dealing with upper limb modelling and trying to get this correct. So a significant portion of, say, the first 10, 12 years of my career was just looking at modelling upper limb motion correctly using traditional electronic and retroreflective systems, and we've certainly moved that from, say, 1995 through to 2020, all the way through, and now we do a lot of this work in OpenSim, like many of you do who are listening today. And as you can see down the bottom, we've moved towards markerless motion capture and a whole range of other things that I'll talk about towards the end of this particular talk. Okay, so someone's asking me a question, I think, so I'll just move along. I'll do those at the end. Okay, so we've actually had about 6 PhDs specifically in upper limb motion capture and modelling particularly. And I would argue probably at least 8 to 10 honours research theses as well. So we spent a significant period of time over those years of 25 years getting this right. And I'm just going to clarify exactly why we need to get it right. So there are a couple of learnings in this particular process that we've now transferred across to wearable technology and certainly our machine learning techniques as well. But getting the basics right, as most of you will know, is paramount. So for this instance, segment definitions were really, really important, particularly with respect to decomposition rules as well. So if you have a look here, if we just remember that was that 15 degrees that was really, really important. We can't go over that 15 degrees. What you're seeing on the screen now is simply the change associated with me defining the first defining line of the anatomical coordinate system differently. So if it was defined using the X or Z or Y axis, that's the result of the extension recording that was achieved. So in one instance there, I would actually be ending a bowler's career simply by the anatomical coordinate system definition that I chose to use. So these things were really, really important, came to be really important, and certainly reinforced my understanding of making sure that I understood exactly what I was modelling before I was ending people's careers over things like a few degrees, which is simply a function of how I chose to model the upper limb. And it wasn't just unique to the elbow, I need to say. So this next example here was a couple of PhDs where we were doing some modelling of the shoulder joint centre. And so this shows you how critical the shoulder joint centre is. We were looking at a whole range of the different methods you can choose to, most of them are regression models, to calculate where the glenohumeral joint centre is located. And I won't go into all of them, but we had a ground truth MRI, and we used this to get a ground truth measure to compare a number of different methods that are available in the literature, Schmidt's method, Vicon's method, and some scapular methods as well. And all I really want to get across from this particular overview is this is the elbow angle on the left-hand axis here. But depending on what shoulder joint centre regression you used, we also used functional methods here as well. Someone could be deemed to be flexing or extending, so you actually get a sign shift at the elbow, simply because, which makes sense, but simply because of the shoulder joint centre method that you used. And we noticed that you could have up to 5 centimetres error based on which shoulder joint centre regression model you chose to use, and that obviously has serious downstream effects when it comes to elbow angles and wrist angles, etc. And I recognise that this may not be of equal importance when it comes to baseball, but when we start to talk about things like the moments about the elbow, particularly with respect to the loads associated with Tommy John injuries and those sorts of things, these things actually do become quite important, because you're starting to see sign changes simply through modelling error, as opposed to actually that don't translate to real world loading patterns. They're not real in the sense that they're just model error artifact. So I think these are things that we need to be really, really aware of. And I must admit, when Vicon first released their overlay of their model procedures, hopefully that will come back, their modelling procedures, which would overlay how accurate your model shoulder joint centre, elbow joint centres were, I did hold my breath for a small period of time, because this was going to be the telltale sign about how well we were actually modelling these joint centres. And as you can see here, this is one of the spin bowlers that we had through the lab. You can see here we're pretty comfortable that we were actually doing quite a good job with getting that right, which is a great tool to be able to check how well your modelling procedures are actually really reflecting joint centres and axes as you go. So obviously after that we transferred across to some wearable technology. I've been doing this for some time now. I'm very aware that there's a significant amount of wearable tech in baseball, and I'm not fully across it, so I don't particularly wish to talk about it. But there are IMU limitations specifically for cricket. I've probably tested nearly all of the systems available, and for cricket bowling in particular, I can say that I don't believe that there's a commercial system on the market that's capable of properly at the high end for elite cricket. That's not subject to signal clipping and saturation currently. There's certainly an opportunity for purpose-built sensors, but at the present time I would argue that we would need a gyro of at least 3,000 degrees a second, 4,000 probably, and accelerometers that are at least 30G to 50G. So at this stage, I'm not convinced, particularly given that we need to use it to offer some high-end, to get high fidelity data back for regulatory reasons, that at this stage I'm not sure wearable tech in cricket is relevant purely because of the accuracy requirements that we're subject to. So, and this is particularly with respect to signal clipping and saturation. But there are two particular process flows that we've been working on for a number of years now that I would like to quickly just mention, and have been doing this with Andrea Cerati and Valentina Camamilla, who are my Italian connections of the University of Western Australia. And there are two things that we can really say have improved some of our outputs when we've been testing this and creating some more anatomically relevant models using IMUs. The first is using functional axes identification. I'm pretty sure that there's a number of people doing this, maybe Arnell in baseball as well, but we're essentially calculating the functional helical, if you like, flexion extension axis, and also the pronation supination axis using the inertial sensors that are positioned on both segments. So we know that actually, when we use those, you can see here, this is a validation study we were doing just of some throwing work. This is Daniel Cottam, who's now at the Australian Institute of Sport, but a former PhD student. And you can see here how well the marker-based system and the IMU system, when you use those functional axes, correlate. And similarly, just in the last year, we've been using this method of Andrea's with Picerno and Capozzo, etc., which is using a calibration frame very similar to that you would use in retroreflective, in using a Vicon system, but essentially putting a sensor inside an anatomical calibration frame and pointing to the relevant anatomical landmarks that you're interested in using. And this also is a really great toolkit to use, especially when you have people with pathologies who have generally non-normative anatomical structures, and also people who are difficult, you're not able to get good segment alignments using your sensors. So this is another approach that could be of use to those people listening. For the future, I want to end on this. I've got about 3 or 4 minutes to go. What I'm currently doing at the moment, and I'm sure there has been some presentations on this sort of work over the last couple of nights for you, is to exploit opportunities associated with AI and advanced computer vision techniques. And to do so, we've been leveraging some large existing data sets. The use case I'm going to give you at the moment is a lower limb example, and then that's only because we haven't moved into an upper limb example as yet, though I'm talking to Glenn about that at the moment, and I'll finish on that particular slide with a potential collaboration. But the next few slides will show you exactly what we'd like to do with respect to something like baseball, which has a large and database of work and vision, certainly vision, but also motion capture tool data that we can actually draw from to do this. So the point of this is, in fact, to bridge the lab to field nexus. So very quickly, what we're trying to do from the data set that we have at the University of Western Australia is looking at some knee loading as it relates to ACL injury. And so we're looking at leveraging our historical motion capture data set and trying to create some machine learning models that will allow us to estimate loads, for example, out on the field. Completely markerless is the objective, so not even using wearable kit. This is, I should do a great shout out right now, don't know if he's online, to Bill Johnson, who's now with the Houston Astros as a data scientist, but this is actually some of Bill's PhD work that he'd done over the last number of years. So for the next few slides, if you have any in-depth questions, reach out to him. But what we did is collated our UWA sports mocap repository. It's about 500,000 mocap files, but we were particularly interested in some sidestepping trials. We took all of this motion capture work, we combined it with the relevant and associated ground reaction force data in both the forces in newtons and also our moments. And essentially what we were looking to do is to create a relationship, so to create a machine learning model that understood the relationship between the marker movement and in fact the ground reaction force. And thanks to Newton, if we can't predict forces or ground reaction forces from motion, we should probably give up the game. So that was essentially what we were intending to do here, and this is exactly what Bill went about doing. And as you can see on the right hand side, just using marker trajectories, we're able to predict ground reaction forces fairly well. As you can see, nearly everything's about 0.9 and moments as well. From there we thought, well, why don't we try and do that with knee moments? Why let's just jump straight past the ground reaction forces and have a look at the loads about the knee. Similarly, that was really successful as well. Still down at 0.7 for our transverse plane moments, but pretty good results, especially for our sagittal plane moments. So that is a direct training a relationship that basically predicted moments directly from motion using a data set of about 3,500 trials. Then Bill decided, well, why don't we bite the bullet and see if we can do this straight from wearables. And this is some work we was collaborative with the Liverpool John Moore's team in the United Kingdom, and similarly we had some great results as well. I'm not going to labour this point. But we've moved on in the last 12 months, and this is some work now of Marvin Martin, Corey Morris, where we've extended Bill's work to basically predict ground reaction forces and moments directly from two-dimensional video, which is machine learning pose estimation. So essentially what we're doing is touching nothing here. We're just estimating ground reaction forces from 2D video. And this is hot off the press. We've only got this out in the last week, but this is what this data looks like. So we did this for walking, running and sidestepping. And I'm just going to race through because I'm a little bit over time. As you can see here, for X and Y, the medial lateral is a little bit messy as you'd expect, but still at 0.8. But we're up at 0.98 and 0.94 for vertical and anterior posterior. For walking, for running, we're still up well above the 0.95s, and also for sidestepping, we're also in the anterior, posterior, and vertical well above 0.96. And so, what does that actually mean for you guys? Well, essentially, you've got huge databases going on with, especially from ASME and motion capture databases, and you also have data related to loading around the elbow and shoulder. So I think there's great opportunity here to do exactly the same thing for the upper limb, and it's something that I'd like to explore with Glenn moving forward. That's all I've got for you this morning. I'd like to thank all of my former students. There's a number of listening now who are at the Yankees and a whole range of places. Hello. And also my collaborator in computer science at UWA, Professor Ajmal Mian. Thank you very much for having me.
Wonderful, awesome. Thank you, Dr. Alderson. Really appreciate it. If you have some time, we do have questions pulling in from the Q&A. So the first question right at the top, Dr. Alderson, you mentioned about cricket. How about baseball pitching? Do you also not feel comfortable about using IMU-based motion capture to track pitching mechanics, K-Vest or 4D motion, if you're familiar with those?
I'm not familiar with those, so I won't pass comment on them. I wouldn't be comfortable with all of those that I've tested for cricket to say that I feel that they would be appropriate for baseball.
Would you have some comments kind of extending off of that, for companies that are looking into these wearable technologies, for application? You mentioned a lot of the calibration, validation work. Do you have some recommendations for those companies as to how to bridge that gap more formally?
No, that's a fabulous question, and we talked about this in Ohio last year with International Society of Biomechanics in Sport. I think I think the companies are in an awkward position in terms of being able to get validation. I think they generally have to reach out to possibly institutions and centres like your own, really. There's not really a go-to place at the moment to assist them with that validation process, although I would like to think that we would come together as an association. We're talking about that at the moment.
For sure. Another question here might be a quick one. In the joint center modeling of the shoulder and elbow, did you notice any change in your bone lengths during the throwing motion? To say, was it modeled to be fixed, or were you mainly focused on joint center accuracy?
Good question. If we're focused on joint center accuracy, you'd like to think that there wouldn't be too much variance in your bone length. But in this type of modelling, there's clearly variance in your bone length. But we generally run two. We used a fixed kinematic length version, but a fixed length version, and then also a traditional approach. A number of our modelling procedures are aimed at reducing that kind of. It's essentially a bone length error associated with soft tissue artifacts. We're very aware of it. We have a number of internal algorithms to try and accommodate for that.
For sure. Maybe one last question here. Do you believe the lack of force plate from pitching would make estimating kinetics more difficult?
No, only if you're talking about lower limb kinetics. I would use an open-ended kinetic model if I was looking at upper limb kinetics anyway, so I wouldn't even, purely because of the areas of flowing kinetics through the trunk. So no, I don't believe that's a problem unless you're looking at lower limb forces.
Absolutely. We'll do one more. All the consistent data would appear to depend on not having an error in marker placement. So again, now looking more on the marker side of things, movement in any direction would alter the data and show inconsistency. How are you taking this into account for consistent marker placement?
Sorry, consistent marker placement is a fundamental issue. So we have a fully trained group within certainly UWA. It's the same model that's actually been rolled out across Australia. When you're talking about machine learning algorithms, though, the movement in any direction, I'm not really sure if the person who's written that means movement in any direction of the person or the markers. So consistent placement is about training. Consistent placement about markers with respect to machine learning algorithms, though, AI, they actually like signal noise and they cope with that variance really nicely. So we have, our entire premise of our lab is based on appropriate marker training and placement. So I'm pretty comfortable that we have a very good system in place to accommodate for that. The person who's asked the pose estimation software, we've run a number, but we also have an internal custom one that we fine-tuned. But at the moment, we've fine-tuned something off OpenPose.
Awesome. Well, thank you so much, Dr. Alderson. Really appreciate it. Really appreciate you taking the time so early in the morning for you. But thank you so much.
Thank you.